Okay, welcome to the mixed calculations overview for gases. Let's take a look first of all at Dalton's law of partial pressures. And here's what it says. The total pressure in a closed system is the sum of the partial pressures of the individual gases in a gas mixture contained within a vessel. In other words, if you had a container that was filled with several different gases, let's just say 3 different gases, the total pressure in the tank would be the sum total of the individual pressures of each individual gas as if each one existed by itself within the container. So the total pressure on the tank is equal to the sum of the partial pressures of each of the individual gases. So let's look at a problem. It says a scuba tank contains oxygen, nitrogen, and helium. The pressure on the gauge reads 2,160 millimeters of mercury. Now, if the partial pressure of the oxygen and the nitrogen are 1,760 millimeters of mercury and 322 millimeters of mercury, what is the pressure in the tank due to helium? So we know the pressures, or the partial pressures of 2 of the gases, the oxygen and the nitrogen. The question is, what is the pressure due solely to helium? Well, we also know the total pressure. It's 2,160. So we can set up the problem as follows. 2,160 millimeters of mercury, that's the total pressure in the tank, minus the sum of nitrogen and oxygen's partial pressure, 1,760 and 322 millimeters of mercury, gives us a total, or a difference of 78 millimeters of mercury. So this must be then the pressure due solely to the helium. 78 millimeters of mercury due solely to the helium. Now let's go on to Boyle's law. The pressure and the volume of a gas are inversely related. Inversely related. P1 times V1 is equal to P2 times V2. Let's look at a problem. The pressure inside a closed can of Coca-Cola is 290 kilopascals. Now a tiny bubble inside the can has a volume of 1.89 milliliters. When the can is opened, the pressure decreases to 101.3 kilopascals. What is the volume of the bubble? So we have here a situation in which the closed can was under high pressure. Once the can was opened, the pressure was released, or at least sent towards atmospheric pressure, about 101.3 kilopascals. So the question then is, what is the new volume of the bubble? Pressure and volume are involved. We know that. And the temperature remains constant. This means that this is a Boyle's law problem. We're going to be using P1 times V1 is equal to P2 times V2. Now we want to know the final volume, so we're going to rearrange. We'll pull the P2 down underneath P1 and V1. In effect, we're dividing both sides by P2. Canceling P2 with P2 on the right-hand side, leaving V2 alone, but now P2 is by itself underneath. P2 is by itself on the bottom. So here's the final problem. We have P1 times V1 divided by P2 is equal to V2 was Boyle's law, set up for solving V2, and we'll plug in now. The initial pressure was 290 times the volume was 1.89, and we'll divide by P2, which is 101.3 kilopascals, and we are ending up with 2.88 milliliters. So this is the new volume of the bubble. It doesn't surprise us that it's a larger bubble since we've released the pressure. We've made the pressure go from a high pressure to a low pressure, and so Boyle's law states that this is an inverse relationship, and Boyle's law states that the bubble should get bigger, and indeed it does, 2.88 milliliters. Let's look now at Charles's law. Charles's law says, given a constant pressure of a gas in an expandable container, such as a piston, temperature and volume are directly related. As the temperature increases, the kinetic energy of the particle increases. The volume must increase to maintain a constant pressure. So here's the formula. V1 over T1 is equal to V2 over T2, which is equal to some constant. Let's take a look at a problem. It says a 12.6 liter balloon is at 26 degrees Celsius. What will be its volume if the temperature is 124 degrees Celsius? How will we approach this problem? Well, we know volume and temperature are involved. Pressure is not mentioned in this problem, so we'll assume it to be held constant. This must be a Charles's law problem. So first convert temperatures to Kelvin by adding 273. So the initial temperature was 26. We'll convert that to Kelvin by adding 273 to get 299 degrees Kelvin initially. 24 plus 273 gives us 397 degrees Kelvin after the changes occurred. So that's 397 degrees Kelvin. So now let's set the problem up. We have V1 over T1 is equal to V2 over T2. That's equal to a constant. And now let's solve for V2. We have V1 over T1, or times T1, I'm sorry, V1 times T2 divided by T1 is equal to V2, is equal to V2. Now let's plug in. V1 was 12.6 times T2, 397, divided by T1, which is 299 degrees Kelvin. So we'll do that division and we get 16.7 milliliters. So the volume then is 16.7 milliliters. 16.7 milliliters. Let's look now at Gay-Lussac's law. Gay-Lussac's law assumes a constant volume. The pressure and temperature of a gas, it states, are directly linked. That is, as temperature increases, the pressure increases. P1 divided by T1 is equal to P2 divided by T2. Pressure 1 divided by temperature 1 is equal to pressure 2 divided by temperature 2. The pressure inside a sealed container is 97.9 kilopascals when the temperature is 298 Kelvin. What will be the pressure if the temperature is 376 Kelvin? How will we approach this problem? Since the volume is held constant and pressure and temperature are involved, we're going to use Gay-Lussac's law. And here's what it says. P1 over T1 is equal to P2 over T1. So let's rearrange and solve for P2. We have P2 is equal to P1 times T2 divided by T1. So we'll solve for P2. P2 is equal to P1 times T2 divided by T1. Now let's substitute. We get 97.9 is P1 times 298, that's T2, divided by 376, that's T1, and that gives us 124 kilopascals. 124 kilopascals. Avogadro's law, the greater the number of moles of gas, the greater the volume that gas occupies. So V1 divided by N1 then is equal to V2 divided by N2. Let's take a look at a problem. It says if 0.42 moles of helium occupies 9.9 liters, how many moles must be added to inflate the balloon to 17 liters? Let's use Avogadro's law. V1 over N1 is equal to V2 over N2. So N2 then is equal to V2 times N1 divided by V1. Then our answer will be N2 minus N1. We have N2 is equal to 0.42 moles times 17 liters divided by 9.9 liters. That gives us an N2 of 0.72, but remember, we're looking for the number of moles to be added. So we'll take that number, the 0.72 moles, that's the final number of moles, minus the initial number of moles to give us the number of moles to be added, and it's 0.30 moles to be added. The combined gas law. This combines Boyle's, Charles, Gay-Lussac's, and Avogadro's law. They can be combined into a single law called the combined gas law. P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. This is the combined gas law. Let's take a look at a problem. The volume of a gas is 200 milliliters at 275 Kelvin and 92.1 kilopascals. Find its volume at STP. You should know the standard temperature and pressure is 1 atmosphere or 101.325 kilopascals and 0 degrees Celsius or 273 degrees Kelvin. From that, we can solve the problem. Now, the combined gas law again is P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. So V2 then is equal to isolated 92.1 kilopascals times 200 milliliters times 273 Kelvin divided by 275 Kelvin divided by 101.325 kilopascals, and that gives us 180 milliliters. 180 milliliters. We're going to be going into the ideal gas law now, and before we do that, we're going to need to know a little bit about conversions of pressure. We need to know that 1 atmosphere is equal to 760 millimeters of mercury, or 760 torr, since a millimeter of mercury in a torr is the same thing. 1 atmosphere is also equal to 101.325 kilopascals, or another way to look at this is then 760 torr is equal to 101.325 kilopascals. So you should be able to make those conversions very easily. The ideal gas law says this. Ideal gases behave according to the ideal gas law, and that's PV equal nRT. PV equal nRT, where P is the pressure, V is the volume, little n is the number of moles of gas, R is the universal gas constant, and T is the temperature in degrees Kelvin. Let's take a look at a problem. It says, how many moles of helium are in a balloon volume of 6.45 cubic decimeters at 99.7 kilopascals and 287 degrees Kelvin? We'll use PV equal nRT. Now we're going to solve for n by pulling the R and the T underneath the PV, dividing both sides by RT, in other words, and we get n is equal to PV divided by RT. We simply divided by R and T, and here we see it again. So n is equal to PV divided by RT. N then is equal to, and we'll plug in. For pressure, 99.7 kilopascals is the pressure. For volume, 6.452 cubic decimeters. R is 8.314 liter kilopascals per mole per degree Kelvin. And the temperature is 287 degrees Kelvin for a number of moles of 0.261 moles. 0.261 moles of gas. Let's take a look at another problem. It says a rigid 8.77 liter tank contains 1.45 moles of oxygen at 20 degrees Celsius. What is the pressure in atmospheres? So we've got PV equal nRT, PV equal nRT. P then is equal to nRT divided by V. nRT divided by V. I take this on top and just divide by V. I'll do the same thing on the left hand side, but as I do, the V's cancel. V over V would be eliminated. So we have P equal nRT over V. Let's start plugging in. The number of moles is 1.45 moles. We're going to multiply that by the universal gas constant. We're using 0.0821 because the pressure was given to us or asked of us in atmospheres. So remember, if the pressure is asked of us in atmospheres, we're going to use 0.0821. The number of that's divided by the number of moles divided by moles divided by Kelvin. The temperature is 293 degrees Kelvin, and the volume is 8.77 liters. 8.77 liters. And when we do that calculation, we get 3.98 atmospheres. 3.98 atmospheres. Let's take a look at this problem. It says, what is the temperature of 12.2 moles of gas in an 18.35 liter tank at 16.4 atmospheres? We're going to express our answer in Kelvin and Celsius. So we're going to use PV equal nRT, since nothing's changing, and this is an ideal gas. We're going to solve for T first. We get T is equal to PV divided by nR. And so let's begin to plug in. 16.4 atmospheres is our pressure. The volume is 18.35 liters. The number of moles is 12.2, and the R then that we choose is 0.0821 liter atmospheres per mole per degree Kelvin. The temperature then is equal to 300 degrees Kelvin. We can subtract 273 from that if we'd like and get 27 degrees Celsius. And that is the ideal gas law. And that is it. We'll see you on the next video podcast. Thank you.